My name is Taylor Marion, and I'm here to present and discuss my project based on large language model based vulnerability detection in tokenized assembly. So the motivation of what drew me to this project is that I've worked in military in cyber operations, as well as a government contractor and in this private civilian world. And I've had a lot of jobs and roles and tasks focused around vulnerability detection. And a lot of the traditional vulnerability detection methods, they often require access to the source code. But there are many instances and circumstances to where you need to find vulnerabilities, but you do not have access to the source code. And there are existing methods of doing this, but each of them have their own little trouble areas. With static analysis and symbolic execution, they both face scalability and coverage challenges, especially for larger, more complicated code. You fall into what's called path explosions. With dynamic analysis and fuzzing, these methods are lengthy, computationally expensive, and imprecise. Because for fuzzing, every time you launch a test, which often takes hundreds or even thousands of tests, each test is a new process being launched. So it's computationally expensive, and there are some fuzzers out there that allow you to kind of create a starting point or fine-tune the fuzzing a little bit, but just by the very nature of fuzzing, you're throwing random garbage data at a process and hoping for a crash. So just by its very nature, it's imprecise. You also have manual reverse engineering, but that's extremely time consuming and requires a very deep expertise. I've done reverse engineering both here with my graduate studies at Dakota State University, as well as a government contractor. And I would not call myself a expert reverse engineer by any means, but I understand that even a basic level understanding of that skill set is not very common in a lot of security teams. So with these factors, compiled binaries remain a critical blind spot for vulnerability research. That leads us into where large language models have a place. They've been shown to have strong pattern recognition capabilities. So the goal here of this project is to determine if we can find those patterns in compiled binaries and detect them in a generalized way, a generic, generalized form that we can then replicate with other compiled binaries to detect those vulnerabilities. So before we go into the specific details of the project, I want to address a couple of the high-level goals here. Number one, this is to assess validity of this approach. I am not aiming to create a production-ready, enterprise-ready, go put this on your network right now product. This is just a test, an investigation for initial feasibility to see if this approach is worth investigating further. For feasibility, it's really important to me that we create something that can be replicated or expanded on by not a large, well-funded team. Many security teams, many security researchers do not have access to their own personal high-powered computing cluster somewhere. A lot of people are going to be doing this kind of research on a laptop or a desktop or some other, small localized system. So I want something that can be used in that way for replicability. Also, because this is a initial investigation into this approach, I am using a very narrow and controlled scope. I'm only targeting a single vulnerability class, specifically CWE, Common Weakness Enumeration 457, use of uninitialized variable. I chose this vulnerability specifically because I've worked with it before, and it is a relatively simple vulnerability. And I'm hoping that the pattern is simple enough to detect and generalize in a broad format. So to get into the actual training of the model, first we need a data set. And for any large language model or machine learning model, you need a pretty sizable amount of samples to put into it as input for the data. So I wanted to find something that was large and cohesive that I could perform in an automated way. I found the Juliet test suite, which is actually originally created by the NSA and is currently publicly available on the NIST, the National Institute of Standards and Technology website. They have this test suite as well as test suites for other languages and many other formats as well. I found a repository on GitHub which expanded on the Juliet test suite and allowed me to compile all that C source code into ELF binaries in an automated fashion using GCC, the GNU C compiler. I then use object dump to disassemble those binaries to obtain a x86-64 assembly instruction set. From there, we had to normalize that disassembly. Now, I chose to use 4 very high-level tokens, which are read, write, end, and no op. This is very simplified, maybe even oversimplified, but for the use case of uninitialized variable, I thought that this is all that we really need, because the vulnerability we're looking for in a nutshell is when a variable is read before it is written to. So it's a very simple pattern. I'm hoping that can be simplified with these very simple tokens. And with some pre-processing output and tokenization, the goal is to get our data in a format that is ingestible for our language model to accept as input. Once we have our data compiled and disassembled and shaped and formatted the way we need it, we then move on into the model training. So the models that we chose here are all variants of the Google's BERT, B-E-R-T model. These are all specifically smaller, minimal implementations of BERT because, like I said from the start, the goal is to build a model that can be replicated on a small individual system. So the Distill BERT by Hugging Face, that's kind of the general best use case that I found, which is replicable. I also wanted to use the Mini LM from Microsoft because it's a similar high performance but small model. Now I should say for the Distill BERT, compared to the normal full-scale BERT model, it retains 95% performance amongst general use case tests, despite needing only 60% of the computing processing power. So it's a good fit for small local systems for training and smaller, less processing power, when computation power is a high concern. I also chose the Mini BERT by Google because it is a very stripped down, very minimal implementation of the BERT model, because I wanted to see if we go as low as possible, like the simplest thing that we can get, how does that trade off for size versus performance? We then move on into model training and fine tuning to classify functions as vulnerable or safe. So at the end of the day, it is a binary classification model to say vulnerable or safe. Our evaluation, we are going to be measuring accuracy, precision, recall, and F1 score, which I think is pretty standard for any kind of statistical or machine learning models. So with our baseline models tested on our training set, we have a pretty clear winner. The mini LM from Microsoft outperforms the other models in every category, and specifically the score that we're really prioritizing here is the F1 score. The F1 score is a good balance between precision and recall, so we're not getting too many false positives or too many false negatives. Once we have our model selected, we're going to go on into hyperparameter tuning. Now, this is where we test different combinations of the hyperparameters to see which combination gets us the best result. We have learning rate, batch size, weight decay, and number of epochs. Now, I want to pay attention to the number of epochs here because this is a little subjective. Too few epochs, you don't get a good enough understanding of the data. If you increase the epochs too high, that can result in overfitting of the data. So 3, 4, and 5 is that Goldilocks range where we can get a good read without being too overfit. This results in a 48 unique combinations of parameters to test for. That did take a while, even using these small minimal systems, these models. That was a overnight, let it run, come back in the morning kind of problem. But after 48 trainings, we did have a clear winner. The selection metric that we were using for these tests was the F1 score, again, to prioritize that balance between precision and recall. So at the end of the result, we have our best configuration that you can see here with a best F1 score of 81.89%. So coming from our baseline to our best, that's a 4 point something percent difference. So meaningful, like 4% is a meaningful difference in that score. So, 81% is a pretty decent F1 score. It's not great, but it's pretty good. But our model does have some limitations that we need to address before we move on. Mainly, we are restricted to a single vulnerability class. Now, that is done for purpose of scope and proof of concept testing, but it's still a limitation we need to address. We also have token normalization, which simplifies real-world instruction complexity. Assembly language is a very rich, complex language instruction set, and trying to reduce all of that down into 4 tokens might be too general, might be too simplified. And these models were trained on a very small, clean data set, where the sample size overall was pretty sizable. I had 1,800 samples in total, 50-50 split between safe and vulnerable. But each sample was a very small, clean source code. They're not full programs. They only really cover explicitly the type of vulnerability that we're testing against. Some are vulnerable, some are safe, but there isn't a lot of fluff code, so to say. The only code present is explicitly related to the vulnerability that we're looking at. There's no optimizations, and there's no packing, there's no obfuscation, so that is a limitation that might present in real-world code. So these limitations offer future work and expansions of this project in future rounds. So we can expand to multiple vulnerability classes for broader generalization. We can incorporate richer disassembly features because in some cases, specific registers might make a difference, especially for assembly instructions. If something uses the register RAX versus RBX, that could make a difference in some vulnerabilities that right now we would not be able to capture. We could also test models on obfuscated code, packed code, optimized code, even code that's compiled by compilers other than GCC. GCC is not the only compiler out there, so we could test if other compilers produce similar enough results to, show the kind of result that we got here with GCC. With these limitations in mind, I feel confident in saying that we have demonstrated feasibility of this approach of using large language models for vulnerability detection. Our best performance with mini-LM reached a 81.89% F1 score after hyperparameter tuning. So these results do suggest that large language models can recognize vulnerability patterns even in abstracted binary form without source code access. So for 81%, to sum this up, 81% is definitively better than guessing. If the scores were only, 50-50, you might as well flip a coin. There's no real winner there. But at 81.89%, that is definitely better than guessing. There's room for improvement. It's not amazing, but I feel like that's a good enough score to indicate that there is potential for this research further. There are some areas of work that we could refine. There are some different models that we could test out. Right now we only use the BERT transformer models, but there are other models that we could use. And these models specifically, they did perform better than I was expecting, or I should say faster than I expected. So even on a local individual system, not using a cluster somewhere, we could potentially use more advanced models and still not have a ridiculously long training time. So there are improvements to be made, but at the end of the day, I think the key insight I want to leave you with is that yes, pre-trained language models do show promise in extending machine learning-based security to compiled binaries without source code access. And with that, I will leave you to reflect, and I thank you for your time, and I hope you have a great break before next semester. Thank you and have a good day.